Welcome to solving trig equations. Before we were simplifying trigonomic expressions and verifying them using trig identities, now we're going to actually solve equations algebraically, kind of piggybacking on a lot of what we've already learned. Alright, let's get right into it. First example here is tan x times cosine squared x equals tangent of x. A really good technique for most of these problems is to first set them equal to 0 and try and solve from there. So let's get this thing set equal to 0. I'm going to subtract tan from both sides, so minus tan x minus tan x. So I'll end up with, on the left, tangent of x times cosine squared x equals, minus tan x equals 0. Now, this still isn't particularly helpful, but it looks like I can factor out a tangent x out of both terms here. So I'll end up with tangent of x times cosine squared x minus 1 equals 0. All right, well, if I want the entire expression to be 0, then either tangent of x has to be 0, I'll be multiplying by 0, or cosine squared minus 1 has to be 0. So let's actually go through and figure these out. Either tangent of x equals 0, got to figure out when that is, or cosine squared x minus 1 equals 0. All right. So this is tangent of x equals 0. Well, I'm going to kind of bring back the unit circle here. We define tangent as, that's a great circle. We define tangent as the slope of the line here. So we would say the tangent of x was the slope of this line. All right, so if I want a slope of 0, I want to know what is the angle that gives me a horizontal slope or a slope of 0 right there. What is that angle? Well, it's 0 degrees, right? So, or 0 radians. So we'd say when x equals 0, right? And since we're looking at this interval from 0 to 2 pi, well, 2 pi is all the way around the circle. So at 0, the slope is 0. At pi radians, right? This is pi radians. The slope is 0. So we've got x equals 0, x equals pi. And then also, like I said, if I'm going all the way around to 2 pi, and also over here at 2 pi, kind of going all the way around the circle, my slope is also 0. Okay, now, those are my two solutions for when tan x equals 0. Very quickly here, I will show you how to solve cosine squared x minus 1 equals 0. This is going to simplify to cosine squared x equals 1. And then if I square root both sides, I get the cosine of x equals plus or minus the square root of 1. Okay, and this is going to be true whenever cosine x equals plus or minus 1. All right, and I'm just going to tell you right now that that is the exact same solutions as when tangent of x equals 0. So the three solutions on the interval from 0 to 2 pi are these three right there. Now, I want you to think about, let's bring up the graph. Okay, so if we think about it graphically, I want to know when tangent of x equals 0. That's going to happen in a couple places. On the interval from 0 to 2 pi, it's going to happen here, here, and here, right? Three solutions. That's when the function is 0. The zeros of the function. When is it plus or minus 1? Well, when is cosine of x plus or minus 1? Well, that happens here at 0. It happens here at a little bit past 3. Well, guess what? That's pi. Excuse me. And when it's a little bit past 6, which is 2 pi. All right, so those happen at the exact same places. Now, if we were to look at the entire number line, all real numbers from negative infinity down to positive infinity, I think that this is going to repeat, the solutions are going to repeat every, let's see, that distance right here was pi, this distance right here was pi. I bet if we kept going, the distance would be pi over and over and over again. So we could also say that the solutions for this are x equals 0 plus pi times k, where k is some constant. Could be -3, -2, -1. It's got to be an integer, some constant integer, right? This would be 2 pi right here. 3 pi would be down the line, and so on. So if I ask for the interval on all real numbers, that would be my solution set. Okay, let's try and solve this one now. 2 sine squared x plus sine x equals 1. I'm going to approach it in the same way as I did the last problem. I'm going to subtract 1 from both sides. So 2 sine squared x plus sine of x minus 1 equals 0. All right. Now this is something that may not be obvious, but we can actually factor it. So this is going to factor into 2 sine of x minus 1 times sine of x plus 1, still equal to 0. All right, now this entire equation will be 0. The left-hand side will be 0 whenever this first factor is 0 or whenever the second factor is 0. All right, so let's first figure out the left-hand factor here. 2 sine of x minus 1 equals 0. Well, that's going to be when 2 sine of x equals 1 or when sine of x equals 1/2. Right? Well, sine of x equals 1/2 is a little bit tricky, but if I'm looking for the angle whose sine ratio is 1/2, and when I think of 1/2, I should be thinking about this triangle, this 30, 60, 90 triangle, where this is, and if it's 30, 60, 90, I think that means our units here are pi over 6 and pi over 3, excuse me, our degree, our angles in radians. Right? And in this side is 1, this side is 2, this other side, the long side, is root 3, but I'm not even going to write it because we're not really worried about it. So whose angle gives me sine equals 1/2? Well, it looks like it's pi over 6. If I use this as my reference angle, pi over 6, then opposite is 1 over 2. So one solution to this is x equals pi over 6. All right, now here's where we kind of drop the, you know what? We're going to go more in depth on this in class. I'm going to give you the other solution. X equals 5 pi over 6. And we will look at why that is more in class. Let's look at the other part now. When is sine x plus 1 equal to 0? Notice it's asking for the exact solutions. Otherwise, we could just take the inverse sine of both sides, right? But since it's asking for the exact solution, we've got to be a little bit more careful. All right, so this is whenever, back to the equation here, whenever sine of x equals -1. This one's a little bit easier to solve. I'm going to kind of clear off this red stuff over here. And just keeping in mind that we've already kind of established that, oh gosh darn it, that these are some solutions, at least on the interval from 0 to 2 pi. When I'm thinking about sine of x, when is that thing equal to -1? I like to bring out the unit circle, all right? And that means when is the vertical height -1? So at what angle, as I kind of move around the circle here, when is the vertical height -1? Well, I think that right here the height is +1, so I don't want that. I want to keep going all the way around to here, all right, when the height is -1, down 1 unit. This angle in red here is 3 pi over 2 radians, all right? So this will happen whenever x equals 3 pi over 2. All right, now, this also wants to look at the interval from -infinity to +infinity, all real numbers. Let's look at the graphs of these two functions and see if we can't figure out when, figure out the general case for -infinity to +infinity. Notice the point I'm trying to make here is that I've got 3 solutions on the interval from 0 to 2 pi. I've got pi over 6, 5 pi over 6, and 3 pi over 2. All right, and we figure that out by setting this equal to 0 and then this equal to 0. All right, let's look at the graphs now. Okay, so this is the graph of sine of x. All right, and I've got 2 situations. I wanted to figure out when sine of x equals -1. That was the one that we did with the unit circle, right? Well, very quickly, sine of x equals -1. That's going to be the intersection of this sine function here, and highlighting it in red, but it's in black, okay? And the graph y equals -1. Those intersect here, here, and so on at constant intervals, all right? So when I say the solution to this, whoops, if I want the solution to this graph, in fact, let's write it over here. If I want the solution to sine of x equals -1, I'm going to take 3 pi over 2. Right? That's what we figured out for one kind of interval from 0 to 2 pi. And this thing is going to repeat, this solution is going to repeat every 2 pi. Right? This distance is 2 pi. This distance right here, those intersections are 2 pi. All right, so we would say take 3 pi plus 2 and add 2 pi every 1, 2, 3, every integer unit after that. So we'd say 2 pi k, where k is a constant. All right, let's look at the other case. Now, I was kind of nice to you, and I gave you that this right here is pi over 6. Yellow is a bad color. That point right there is pi over 6. All right, and I told you also that this one was 5 pi over 6. And if you notice here, that from 0 to 2 pi, that's it. There's no, that's 2 pi right there. There's no other intersections between 0 and 2 pi. But look what happens over here. I've got another intersection and another intersection. All right. If I just worry about just this pi over 6, the distance between pi over 6 and the next one, wow, that's a lovely brace there. That distance is going to be 2 pi. All right, so let's write this down. Pi over 6, so when x equals, so this is true when x equals pi over 6 plus 2 pi k. All right, this next one is going to be true when x equals, now no longer are we looking at the pi over 6 situation. We want to look at the 5 pi over 6 situation. This is 5 pi over 6. Okay, if you're doing this on your calculator, you're going to get some nasty decimal. But I'm saying, hey, when you find that nasty decimal, it's this point. All right, and the distance between that one and the next time that the next interval of pi over 6 is 2 pi units. That happens. It's because the period of sine is 2 pi. It happens every 2 pi. So we also have 5 pi over 6 plus 2 pi k. So if I'm looking at the solution generally for all real numbers, I've got 3 things going on here. I've got, oh, that was a disaster. Sorry, bring it back. I've got this solution here, and why does that keep happening? I've got this solution here, 3 pi over 2 plus 2 pi k. I've got this solution here, x equals pi over 6 plus 2 pi k, and then this solution here also. Oh, mommy, what a sweet problem. Like I said, we'll explore that interval idea more in class tomorrow. Otherwise, you're ready to solve some trig equations.